Hello. My name is Mark, and I am a contributor to Optimism. Thank you for coming today. So the last few times that I gave talks, they were pretty in the weeds. They were really focused on the technology. This time around, I want to talk about something a little bit higher level. So my talk is called Design Decisions Shaping L2. Right? So my claim is that user stories help us solve real-world problems. Basically, today we're in this industry where we love talking about the technology, and we go super deep into the weeds about these crazy tech solutions without first contextualizing what the problems are. So really, I want to go back to first principles and think about the actual problems framed as user stories. Because if we don't do this, we might end up building technologies that don't actually solve problems and have real value propositions. So, I'm not a product person. I literally have no idea what I'm doing, but I'm here to talk about user stories. So, what is a user story? A user story is a brief description of a software feature or requirement articulated from the end user's perspective, right? The end user, right? This is framing things in terms of solving problems for end users, right? So, we don't need to care a lot about the technical details. We just need to care about the problem that's being solved and the value that is going to the end user. So a good way to frame a user story is, as a who, I want what, so that why. And I would love to just, invite everyone in the audience to reframe the way that they're thinking about blockchains in terms of user stories. So this is my take at creating some user stories specific about the OP stack. So the first question that we want to ask is, who is our user? And in all startups, this is an incredibly important question, because if you don't know who your user is, then you don't know what problems you're trying to solve. You're going to be really unfocused, and you're not going to be able to actually build a product that people want to use. So for right now, we're going to say that our user is an entity with on-chain assets. All right, so we're going to go through some value propositions, and we're going to start with censorship resistance. So as a user, I want to be able to guarantee that I can include a transaction so that I can maintain the ability to exercise property rights over my assets. So why is this important, right? We want, you could imagine you're a user that has a loan and you need to keep it collateralized during times of high volatility. And if you can't, land that transaction, you might get liquidated and lose a bunch of money. So we have a solution. We call these force include transactions, right? And basically in the OP stack, as an L2, there's two ways to include transactions. There's the low latency way, where you send the transaction directly to the single sequencer, or there's the more censorship resistant way, which is you go through L1. And either of these routes allow you to do an arbitrary action on the L2. So the worst thing that the sequencer can do in this case is delay the inclusion of your transaction, right? So the sequencer can delay your property rights over your assets on the L2, but the sequencer cannot fully prevent you from accessing your assets on the L2. And this became apparent when Sonium was censoring at the level of the sequencer. users were still able to access the meme coins on the L2, even though the Sonium sequencer wanted to prevent IP infringement. So the OP stack is built in a way to give censorship resistance. It's really just about the latency of that inclusion. And it is an engineering problem to lower that latency over time. Okay. The next one is around hardness. So hardness is this thing, people from the Ethereum Foundation like to talk about this, but really it's about the hardness of a platform is about the immutability of it, the understanding of how it's going to respond given an input or in certain situations. But basically, if we think of it in terms of the user story, as a user, I don't want the rules of the platform to change underneath me in a way that is not aligned in my interests, so that I can rely on the platform in life or death situations. Right? This is one of the promises of, Web3 or crypto, where you understand the rules of your counterparty. And, you can kind of think of it like Web2 platforms like Reddit, for example, right? Like their governance rules can arbitrarily change. And it's like the same with Facebook. And you really have no say. You're just stuck at the will of the, governing platform that owns that owns the platform. And we're trying to build systems where it's more transparent, it's more open, and it's more participatory. So, solution, we got the roll-up stages framework, right? So, the delayed upgrades. And in stage 1 and stage 2, right, we have the 7-day delay on upgrades, and then stage 2 has the 30-day delay on upgrades. So, what does this mean? If you don't like a change to the system, you have the right to exit. And you can take your assets with you, and then you can take them to another chain. So it might be difficult, the same way that, let's say that you have like a really high karma score on Reddit or something. It's really difficult to make that portable to another social media app. Ideally, we can think about designing applications in a way where that sort of information is portable, and you can exit your application, or you can exit your reputation and go take it to another app on a different chain. So we have delayed upgrades. Now, something that people have been asking about recently is, what if the sequencer arbitrarily decides to change the rules of the chain? This is something that, it's not really clear. People kind of have this intuition that the sequencer has the ultimate right to set the rules of the chain. But with the OP stack, this is not true. Because if the sequencer decides to unilaterally issue a hard fork, the old chain still lives. And the bridge honors the old chain. So the sequencer can't just automatically push an upgrade and enforce everyone to follow those new rules. They will get reorged. The protocol, right? This is like the reason why you run a full node. The full node like validates the rules of the blockchain, right? So the sequencer will itself be reorged by like the real rules of the protocol. All right, so now let's talk about medium of exchange. So as a user, I would like to use my on-chain assets to purchase real-world goods with as good of UX as a credit card so that I can rely on blockchains for everyday expenses. I'm really looking forward to the day when I can actually just use blockchains every day and just move my money on-chain and, just live on chain. one day. So, solution to this. We have levels of finality, right? This idea of pre-confirmations, and then like Ethereum inclusion, and then true economic finality. So in the OP stack, we call pre-confirmations like, unsafe blocks. We have a single sequencer that basically commits to the next L2 block and sends it over this peer-to-peer network. And this exists for the user experience of I send my transaction and it's included and I can instantly see it on Etherscan. Right? That's to an end user, they need to see it on a block explorer or something to know that it's real. Sometimes people even think that if the block explorer goes down, the chain itself goes down, right? So seeing it is really, really important. It's like this psychological thing. So the reality is that, Ethereum has this 12-second block time. And for the OP stack, finality is when your transaction data is that the user sends their transaction to the L2, and then the sequencer will then take those transactions that are sent to the L2 and then include them in a batch and send that batch to L1. That is when the L2 finalizes. A lot of people have the misconception that the L2 actually finalizes after 7 days, and that is not true. It only takes inclusion of the batch. So the L2 can finalize at as fast as L1 finalizes. So we have, and because Ethereum blocks are 12 seconds, you can't get that good user experience of instantly seeing your transaction on Etherscan. So this is why pre-confirmations exist. And there's many different ways to do pre-confirmations. The community is really excited about this idea of based pre-confirmations. People are now kind of arguing about gateways and other things like who knows what's going to happen and shake out. But today we know that at least in the single sequencer model, it is working. Basically, the single sequencer signs off on the next L2 block, sends it off on the P2P network, and then they take that block and then they put it into a batch, send that batch off to L1, and then it finalizes that L2 block. So next one, let's talk about liveness. So as a user, I would like to not rely on the uptime of a third party so that I can always rely on my on-chain assets. So basically, a lot of people think that an OP stack chain goes down if the sequencer is down. In reality, an OP stack chain stays live. It continues processing blocks. It's just much, much slower. There's this kind of liveness gadget that's built into the OP stack where if the sequencer goes down and stops posting batches to L1, then the network will automatically start producing blocks. And this is how you get the guarantee that the network always stays live. So we have this idea of a sequencing window, which is 12 hours. So what this means is if the sequencer has not posted a batch in 12 hours, then the chain starts producing what we call deposit-only blocks that only include the forced inclusion transactions. So what this means is if the sequencer goes down, you can still interact with the chain at a much lower latency, or higher latency, sorry. So if the sequencer goes down and you want to withdraw your assets, you can use a force include transaction to withdraw. You can really use this force include transaction to do anything on the chain. So this website, bridge.gg. You can, come to this website and you can, click advanced expert mode, and then they give you a few options, right? You can click this custom transaction mode, copy and paste an ABI in, and make literally an arbitrary call. So this tool exists. Anybody can do it. So if you're worried about being censored, this right here is how you interact with an L2 in a censorship-resistant way at the latency of L1. So specifically with withdrawals, you can initiate a withdrawal through this pattern, but you need a permissionless proof system in tandem, because the permissionless proof system enables you to keep the bridge alive. In the context of a fault proof, this means that anybody can come and make a claim about what the L2 state is. So this is basically how an OP stack chain is always live, so that a user can withdraw if the sequencer goes down. Next is MEV protection. So a big problem on L1 is, this dark forest where people like, Jared from Subway, they sandwich users and extract MEV. And this is not good because users lose money, right? So as a user, I would like to transact without being worried about being sandwiched so that I don't leak my value. So in the OP stack, the solution is a private mempool. So the idea is that if only the sequencer learns information about pending transactions, then it's only the sequencer that has the ability to do the sandwiching. Now, people might not like to hear that, but if we think of it as, say, an iterated game where it's based on the identity of the sequencer has reputation to lose if they start extracting a bunch of MEV. Now, this might not be a good enough security model for you because past performance doesn't indicate future performance. The sequencer might just wait until the right moment and extract all the MEV and then basically exit the market. So what you can do here is run the sequencer in a TE. I think that this is a very good spot in the trade-off space where if you run the sequencer in a TE and you make it very legible what the exact block building algorithm is, then I believe that this is purely creating value, right? When you run a sequencer in a TE, you can say this is the specific block building algorithm that is being used. And users that might not be sure if they want to interact with the chain, they will have a strong guarantee that they know what the block building algorithm being used is, so they'll know that they won't get sandwiched, and they know that they won't get front run. Right? This is Unichain with their whole flash blocks and rollup boost. The idea is that by making it public information that all blocks will be built with priority fee ordering, so like sorted based on fees, the tip paid to the sequencer. By making this public information, everybody knows the exact game that is being played. And they don't have to worry about somebody being sneaky behind the scenes, right? That's like one of the most difficult things about the MEV landscape is that you never really know where the order flow is going and where the information is leaking to. So the set of possible games being played is kind of boundless. So now I'm going to talk a little bit about the write costs. So this is transaction fees. So the user story here is, as a user, I'd like my fees to stay consistently low so that I'm never priced out of being able to exercise the property rights of my on-chain assets, right? Like this is like a good example of this is like if you're using like the Lightning Network, for example, and you always need to have enough fees to be able to close your channel. And if the fees on L1 go up, then it like pushes up the cost of closing your channel. Now you can't like have like a channel with like only a little bit of value, kind of defeats the value prop. Okay, I got a little in the weeds there, but generally we need fees to stay low at all times so that users can always easily access their assets. So the idea that we're building in the OP stack is horizontal scalability. So we do need to assume that DA is solved, and that's not an easy assumption to make, but for this conversation, we'll just say, DA is solved, and it's really execution is the bottleneck, right? We want to start thinking about applications in terms of a horizontally scalable set of microservices where every new chain that you add to this Interop cluster enables additional throughput for your application. And this is the only way that we will be able to scale to global demand, because it is just not realistic at all to have a single server that is able to process all of the transactions of the world. So the idea is, with this cluster architecture, it's many chains that all kind of come together as a single chain. And it's basically just parallelism. Each block is producing, or each chain is producing blocks in parallel. So now we can also think about app developers as our user, instead of just end users that send transactions to the chain. So EVM equivalence, this is a great value prop. As an app developer, I want the Ethereum tooling to just work with my app deployed to L2 so that I can focus on application development instead of rebuilding my tooling stack. So one of the design decisions or principles around OP Stack is to make sure that tools like Foundry and Hardhat just work. So we don't add any extra precompiles or giant modifications to the EVM or state transition function so that we can guarantee these developer tools just work. You want to have as little overhead as possible for your developers coming onto your platform. Like, for example, like even things like Tenderly, like having Tenderly be able to show the whole traces and as a developer being able to go to Tenderly and, have it just work because it's EVM equivalent and it doesn't have anything crazy in it, is like a big value prop. So yeah, we always make sure that, tooling for L1 works on the L2. Now another one, in terms of interoperable apps. So as an app developer, I don't want to have to worry about complex interop details so that I can just focus on my application logic. So what does this mean? It means that we want to make it so that cross-chain calls are as similar to EVM calls as possible. We don't want to introduce new concepts. We want to be able to just give developers a simple library that they can just import into their Solidity app and just use this library and have it just work. They shouldn't have to learn anything crazy about the, protocol itself. They shouldn't have to, make huge modifications to their app. So the idea is that these cross-chain calls, we want to make them very similar to like an Ethereum call, like within the EVM. So we have this idea of contingent reorgs. And contingent reorgs basically exist to remove the need to think about cross-chain finality. If you're an app dev and you had to implement custom logic per chain, thinking about like what is the finality of this remote chain that's like bringing in an inbound message, that would be really complicated. And we don't want developers to think about that. We kind of want it to just be homogeneous and to just work. So the idea is that these contingent reorgs mean that the chains reorg together. And that's very similar to within one chain, your subcalls, like, if the chain reorgs, like all of them reorg together. Cool. And that's it for my talk.
We can take a few questions as we're setting up next speakers. Is Sriram here? He's right there. Okay. Any questions for Mark? Here we go.
How do you balance the complexity of contingent reorg? You have like n roles that are all interacting with each other.
Sriram, let's get you set up. Hey.
Yeah, I mean, that is a great question. Basically, we are more interested in thinking about it in terms of correctness. So there really is no bound to it. I think really it's kind of just like, so at least the way that we've been thinking about it is the sequencer takes on risk by accepting cross-chain messages. And for the app developer, the app developer wants to think about all of the chains as like being fungible, like their security properties. So they don't need to like worry about, differences. And they can just write one application that is just interoperable. But the sequencers, they kind of take on the risk, because if they they can accept inbound messages that have pre-confirmation level of security, or they can accept inbound messages where like the data has been batch submitted. Like those are two possible things. And really it's up to the sequencer to decide if they want to accept the pre-confirmation or if they want to accept it only after it's been batch submitted. Yeah, like there's like some, reputation, right? If you are causing other chains to reorg, like those chains may not want to accept inbound messages from you anymore. But really what I'm getting at is there's tools that chains and sequencers can use to reduce the risk of these contingent reorgs. There technically is no upper bound on the complexity of one. And I think really it's about finalizing your data and not accepting inbound messages from chains that are high risk to reorg.
Either the chain takes a hit from another chain reorging, and now the message is being consistent, or the application. Right? So somebody's still taking a hit, whether you reorg together or not. I don't know.
Yeah. I mean, ultimately there's risk someplace. And we believe that, we want to build the best developer platform, and that chain operators or sequencers, they are much more specialized and they can build the, DevOps and the software required to like make sure that there aren't reorgs. So yeah, I think simplicity for the developer over simplicity for the chain operator.